All right, so this is question 8.9, and it's about a turbine. We're told that steam, initially at 7 MPa, 600 degrees C, and 75 meters per second, enters an adiabatic turbine. That's an important piece of information. We're told that the turbine is adiabatic. And it leaves it at 50 kPa, 150 degrees C, and 300 meters per second. If the power output of the turbine is 5 megawatts, what are the mass flow rates of the steam and the isentropic efficiency of the turbine? So what I have not brought up yet, I have not brought up the notion of isentropic efficiency. So what the isentropic efficiency is telling us, what they're asking for, hold on, let me sketch it. So this is H. Should I do it as HS or TS? I'm going to sketch it as TS, I think. Yeah, I'm going to sketch it. Okay, so if we throw back to when we were talking about the Rankine cycle, okay? Actually, it'd be easier if I just discuss it here. So when we were talking about the Rankine cycle, we were talking about isentropic turbines, which means that if I look at a TS diagram, we drop as a straight line from 3 to 4, okay? This is the process that we would expect. There we go. Okay. So this here is the turbine. This is where the turbine happens in the Rankine cycle. In reality, the process is not going to be truly isentropic. There will be a small increase in entropy, okay, because that's how things are naturally. For things to flow, the entropy will increase. So in reality, this is 4S, so this as if the system was isentropic. In reality, we will end up somewhere over here. So I would call this 4 prime or 4 real. Anyway, the nomenclature isn't really important, but in reality, there will be an increase, a small increase in the entropy, okay? So if we look at all of the information given in this question, we see that P1 is equal to 7 MPa. We know that T1 is 600 degrees C, and we know that the velocity was 75 meters per second. All right, I know that the P2 is 50 kPa, that T2 is 150 degrees C, and that the V2 is 130 meters per second. Is there anything else that we need? I know that the work of the turbine is equal to 5 megawatts, which if I want to convert into kilowatts, because it's the unit we normally work with, everything is in kilojoules, we're going to know that it's 5 times 10 to the 3. So the first part of the question is asking us to find the mass flow rate. And I'm going to start with that because this is a little bit the easier part of the question. And what will give us the mass flow rate, you ask? It will be the first law expression. So I'm going to need to use, again, steam. So therefore, there's tables that we can use, which are nice. So from this, I'm going to see that H1 is 3650.3 kilojoules per kilogram, and I'm going to see that S1 is 7.0894 kilojoules per kilogram Kelvin. This is from the superheated. If I look at these properties again, at this stage here, I'm also using the superheated tables because you're going to see if I look at this value for temperature, so at the pressure is equal to 50 kPa, you'll see that T2 is greater than Tsat, therefore we must be superheated. Because sometimes at the outlet of a turbine, you would expect a mixture, but in this case, it was still superheated. So we're going to see that H2 from the superheated table was 2780.1. So what I'm going to do is I'm going to run out of the room, is I'm going to start by solving for the mass flow rate. Give myself some room. All right, so I'm going to start by solving for the mass flow rate. So I'm going to need to look at the first law equation. So what I'm going to do, again, we know there's no change in total internal energy. We know it's adiabatic. Turbines, however, are going to do work, so that's good. And then I have a mass flow rate, which is unknown to me. And I have an H1 minus H2, my enthalpy at the inlet, my enthalpy at the outlet, velocity at the inlet, velocity at the exit. So what I'm going to do is I'm going to isolate for M. So my M dot is work divided by H1 minus H2 plus V1 squared over 2000 minus V2 squared divided by 2000. And now all I have to do is substitute in all these values because they're all known. So I know my work was 5 times 10 to the 3 kilowatts. I know that my enthalpies I was able to find from the tables. So I had 3,650.3 minus 2,780.1 kilojoules per kilogram. And then I'm going to say plus, oops, my line, okay. Oh no, all right. Give myself the room that I need to work, all right. And then my velocities, so it's going to be 75 squared minus 130 squared meters per second divided by 2,000. Right, that's to convert between joules and kilojoules. This will give me a mass flow rate of is equal to 5.783 kilograms per second. Okay, so I paused to double check the tables. And so now we're going to start, we found the flow rate, which was the first part of the question. That was the easy part. Now we're going to try to find the isentropic efficiency. If you look at pressure and temperature, you will indeed see that it must be superheated at this stage. Okay, so this is our 0.4, this is our actual here. So in reality, our gas is still superheated, which is a little bit unfortunate. Normally, we would like to extract a little bit more work from it, right? And normally, we would assume that the turbine is isentropic, okay? So this here is my H2 actual. This is the actual enthalpy at the end, all right? I looked at the tables, I know the pressure, I know the temperature, and I was able from that to extract the actual enthalpy at the end of the stage, at the end of the turbine. But what I would like to know is in an ideal turbine, in a perfectly isentropic turbine, which is not really possible, but what is this 4S point? Where is that going to be? Okay, and that is what I'm going to need in order to find my isotropic efficiency. So now I'm going to assume a perfectly beautifully isentropic turbine. So assuming it is perfectly and beautifully isentropic, I'm going to assume that S2 is equal to S1. So from this, I'm going to, assuming that S2 is equal to S1, I'm going to need to find the quality of the system at that point. So I know that S2 is equal to S1 is equal to SF plus X SFG. And this was solved using the pressure table. So at P equal to kPa. Why did I use the pressure tables and not the temperature tables? The temperature here, you can see where, because these lines are constant pressure, right? So this line here is at 7 MPa. And this line is at 50 kPa. And these pressures are known, all right? The temperature will change slightly depending on the isentropic efficiency. Because if I'm really inefficient and I wind up somewhere here on my isobaric line, my temperature will be higher than if I had a good isentropic efficiency, right? There is going to be a change in temperature. So for that reason, I'm going to, for the sake of my beautifully isentropic turbine, I'm going to ignore the temperature value, okay? Because the temperature value is going to be dependent on my isentropic efficiency. Isentropic efficiency, my goodness. All right, so I'm using the pressure tables to solve this. And I'm looking for my X. This is known. SF and SFG and S1 equal to S2 are all known. So my S1 equal to S2 was 7.0894. My SF from the pressure table was 1.091 plus X 6.5029. This was SF, SFG. And this gives me a quality of 0.2, oops, oh, no, 92, not 29, 9224. What this means is, if my turbine was beautifully isentropic, it would be able to remove enough work, it would be able to produce enough work so that my gas, or my mix, or my water at the outlet is in a mixture phase. It is no longer superheated. All right, so the beautifully isentropic turbine is capable of doing more work than my actual turbine, which is the values that I had in the question. So for my isentropic turbine, this is the quality that I get. And using this, I'm going to find my HS2, or H2S. So this is the entropy, this is my, this here is going to be the enthalpy at the exit of the turbine, assuming my beautifully, perfectly working isentropic turbine. So that value is going to be equal to HF plus XHFG. These again are numbers coming out of the table. So HF is 340, again, out of the table at the 50 kPa. 340.49. Actually, these units, kilojoules, I didn't write them, kilojoules per kilogram Kelvin. Plus X 0.9224 times HFG is 2,305.9 73.4, this one is kilojoules per kilogram is my unit. And it gives me an enthalpy of 246. 7.0 kilojoules per kilogram. So my isentropic efficiency is defined as my actual work, or my actual enthalpies, right? So it's going to be we're going to be talking about the actual enthalpies over the isentropic ones. So my actual this is my actual work. We're going to be talking about actual work here and isentropic work. So the actual work we've already calculated, that was good. So now I'm going to calculate how much work can my isentropic turbine do. So work done by isentropic turbine. Again, I'm going to need some more room. All right, so I'm going to look at my first law equations again when we're talking about work. So no change in total internal energy, no, it's adiabatic, does work, m dot, we have a flow in and we have a flow out, we have a velocity in, and we have a velocity out. So what this means is my work going to be equal to the flow rate, which I calculated earlier. There was a reason we were asked to calculate it. So 5.783 kilograms per second. And now this is my H2S. All right, this is my isentropic turbine, my beautifully functioning isentropic turbine. Now I'm going to look at how much work it would make. So 3,650.3 kilojoules per kilogram minus 2,467 kilojoules per kilogram plus my velocity at the beginning, 75 meters per second, minus my velocity after, 130 meters per second. Converting them into kilojoules gives me a work of 6,810.42 kilowatts. So this isentropic efficiency is going to be the actual work done divided by the isentropic work. So my actual work done was 5 times 10 to the 3 kilowatts. And my isentropic turbine could, in theory, produce 6,810.42 kilowatts, which gives me a turbine with an isentropic efficiency, 73.4%. You can also look at it as H2 minus H1. This is the enthalpy change of the actual turbine over the enthalpy change of the isentropic turbine. So those values, I had them at 2,780.1 and then 3,650.3. These are kilojoules per kilogram. And then with my isentropic enthalpy, you'll see that I get calculated it, did I not? Yes, 2,467.0 minus 3,650.3 kilojoules per kilogram will give me an efficiency of 73.5. Well, we'll take the rounding, a little bit of rounding involved there. But that is my isentropic efficiency of a turbine.